So in this lecture, we will be explaining uh, about a device by which we can create different states of polarization. Okay. Okay. So that the name of that device is called retardation plate. Okay. So what is a retardation plate? What is this device? This device is nothing but a optically anisotropic crystal whose optic axis is parallel to its refracting surface. Optic axis is parallel to its refracting surface. Okay. Now, in the previous lecture, we have learned that if a linearly polarized light falls on this particular crystal with angle of incidence 0 degree, when it will be coming out of this crystal, we can get different states of polarization. Initially, it was a linearly polarized light. When it is coming out of this crystal, we can get different states of polarization depending upon which factor. If we remember correctly, then this was the scenario. Okay, before entering the crystal, ex and ey component has no phase difference between them, but after it enters the crystal, when it leaves the crystal, the ex component, which is now the e ray, and ey component, which is now the o ray, because we have already explained, x component is vibrating parallel to the optic axis, y component is vibrating, the light vector is vibrating perpendicular to the optic axis. That's why this is o ray and e ray. O ray and e ray traveling through optically anisotropic crystal, they have acquired a phase difference between them. We call that phase difference to be delta, and depending upon this delta, we got the master equation that I am calling it as a master equation. That master equation is giving me different states of polarization depending upon two parameters. One is definitely delta, another one is theta. That is here inside E naught x and E naught y. What was it? E naught x was equal to E naught cos theta, E naught y is equal to E naught sin theta, where theta was the initial angle that the light vector was making with the optic axis of the crystal. Okay, this initially it was a linearly polarized light, so the light vector was making this constant angle theta with the optic axis of this crystal. Okay, so this is the full story. So now, if I really want to create a device that controls my states of polarization, then I need to create a device that can control delta and theta. Achha. By the way, theta can be controlled very easily. Let's say this is the direction of vibration of the light vector. Let's say this is the direction of vibration of the light vector, and this is the optic axis. Now, if I rotate the crystal, so optic axis is also rotating with the crystal. I can align them. Okay, so theta can be controlled, or I can change the theta. If I rotate the crystal, then I can change the theta. That can be done very easily. We don't need any device. Okay, this crystal can be rotated to change the theta. So theta story is over. Now, how to control delta? So if we want to understand how to control delta, we need to understand that why this delta comes. This delta comes because this O wave surface, wave front is circular in nature, and this E wave surface is elliptical in nature. So this O wave and E wave is traveling through this crystal, and as long as they travel, they will keep on acquiring this phase difference between O ray and E ray. Okay, so on which factor this delta depends? As long as the wave will be traveling inside this crystal, there will be phase difference acquired. That means this phase difference delta depends on the thickness of this crystal. Let's say D is the thickness of this crystal. Okay. Now, if D is the thickness of this crystal, then if we can control D, we will be able to control delta. Okay. Before going into anything else, let us remember again that if delta is pi, then this light will be linearly polarized. The output light will be a linearly polarized light. If delta is pi by 2 and theta is pi by 4, theta is 45 degree, then the output light will be a circularly polarized light. And if delta is pi by 2 and theta is not equal to pi by 4, the output light will be elliptically polarized light. Okay, so this was explained in the. What is this delta again? Delta is the phase difference between x component and y component for this particular case. That means O wave and U wave. Delta is the phase difference between them. Okay. Now let us see if delta is equal to pi, then I will be getting linearly polarized light. Okay, fine. Now we how to control delta and what is the dependence of this delta on the thickness of this crystal. Now if this O wave and U wave is are traveling inside the crystal, they will be acquiring a optical path difference between them. What is the optical path difference between this O wave and U wave? Optical path का definition क्या है? Optical path is refractive index multiplied by the physical distance. Okay, so the optical path difference between the O wave and U wave will be given by mu e difference mu o into d. D is the thickness of this crystal. Okay, difference क्यों लिया? Difference for the reason difference because we don't know, we can take a optically positive crystal as well as optically negative crystal. So this should be a positive quantity, optical path difference. Okay. Now if optical path difference is known, then the phase difference, how do you calculate? 2 pi phase difference corresponds to lambda of optical path difference. Okay, so delta phase difference, if the phase difference is delta, then delta is given by 2 pi by lambda into capital delta. Okay, so this is simple. So we need to remember these two formula very nicely. So capital delta, that is the optical path difference, that is equal to mu e difference mu o into d, and small delta, that is the phase difference between the O wave and U wave, that is equal to 2 pi by lambda into capital delta. So these are the two basic formula of retardation plate. Okay, now we need to get a phase difference of pi if we want to generate linearly polarized light, and we need to get a phase difference pi by 2 if we want to generate circularly polarized and elliptically polarized light. Then theta we can adjust. Okay, so these two, I want to create two devices. One will be giving me a phase difference of pi, another one will be giving me a phase difference of pi by 2. Now let's see, if the phase difference is pi, delta, small delta is pi, then capital delta is given by capital delta equal to lambda by 2 pi into small delta, lambda by 2 pi into pi, that is lambda by 2. Capital delta will be lambda by 2. Now capital delta means mu e difference mu o into the actual physical thickness of the crystal. So let's say that what is the minimum thickness that is required for the crystal to acquire this optical path difference, that is mu e difference mu o into d mean, that is equal to lambda by 2. Now that means the d mean, the minimum thickness required by this crystal to get a phase difference of pi, that is path difference of lambda by 2, is given by lambda by 2 into mu e difference mu o. Now as this is lambda by 2, we call this particular retardation plate as half wave plate. Okay, we also need to generate another retardation plate that will be giving me a phase difference of pi by 2. Now if the phase difference is pi by 2, then the optical path difference is definitely lambda by 2 pi into pi by 2, that is lambda by 4. Okay, so the minimum thickness optical path difference is again mu e difference mu o into d mean. If d mean is the minimum thickness of the crystal, so d mean equal to lambda by 4. That means d mean is given by lambda by 4 into mu e difference mu o. So this, because of this lambda by 4 term, we call it a quarter wave plate. So this is a quarter wave plate and this is a half wave plate. So inside the in lab we have these two devices. One is half wave plate. So if a light enters through a half wave plate, that means there will be a pi phase differences incorporated between the two components of the light vector. And if light is enters inside a quarter wave plate, when it will be coming out of the quarter wave plate, a phase difference of pi by 2 will be inserted between the two components of the light vector. So this is the basic of retardation plate. Now let us explain an example by which we will be understanding how can we change the state of polarization if we have these two. You have quarter wave plate and half wave plate in the laboratory. Now where to use which retardation plate? Let's say you have a linearly polarized light. You want to create a circularly polarized light. So which retardation plate to use? Okay. Now, how to approach this type of question? That means immediately after you have this question, you have to understand that what is the phase difference between the two components, O wave and E wave. So if it is a linearly polarized wave, either the phase difference is equal to 0 or pi. Okay, either. So that is the phase difference between the O ray and E ray. Initial phase difference. You want to create a circularly polarized light. You want to create a phase difference of pi by 2 to create a circularly polarized light. Okay, so extra amount of pi by 2 phase difference is needed. Okay, so that means you will be using a quarter wave plate, but that is not, doesn't tell you complete. It can be a elliptically polarized light also. So you have to mention that theta has to be equal to pi by 4. Then it is certain that it will be a circular. And now, if you want to create an elliptically polarized light, you have to use a quarter wave plate again, because you need to insert pi by 2 phase difference, and also you have to make sure that theta is not equal to pi by 4. Otherwise, it will be a circularly polarized light. Let's say you have a circularly polarized light, you want to create a linearly polarized. Circularly polarized light means initial phase difference is pi by 2. Okay, you want to create a linearly polarized light. That means delta equal to pi. Okay, to get a linearly polarized light. So another pi by 2 phase difference. That means you have to use a quarter wave plate. Okay, elliptically polarized light, delta equal to pi by 2. Okay, you want to create a linearly polarized light, so delta equal to pi. Again, you need to pass this light through a quarter wave plate. You have a right circularly polarized light. You want to create a left circularly polarized light. That means you need to incorporate a pi phase difference between the two components. Whatever be the phase difference, initially it was phase difference was pi by 2. Okay, finally also phase difference has to be equal to pi by 2. Okay, but the direction of rotation has to change. So if you want to change the direction of rotation, then a extra pi phase difference is needed. So you will be using a half wave plate here. Okay, left circularly polarized light to right, again half wave plate. Okay, let's say you have a linearly polarized light which is vibrating like this. You want to create another linearly polarized light which is vibrating like this. You want to change the plane of vibration basically. Okay, so you have to incorporate another pi phase difference here. So you will be you have to use a half wave plate. Okay, so this ends the theoretical description of this chapter of polarization. Next video I will be explaining a few numericals, and we will be done with this chapter polarization.